Hello everyone, welcome back to my first review video on AP Physics 1, and this is Unit 1. And let's begin with reviewing units. So units are reference standards of a quantity. The common unit are SI unit, and some countries are using the British system such as US. The prefix are for decreasing the numbers of numbers when writing a specific quantity. So basically what unit is that a number how many times larger or smaller compared to a standard reference unit. And it's given in the equation sheet right here. Hertz, joules, kilogram, meter, Newton, Pascal, second, and watt. And here are the common prefixes given in the equation sheet. And now let's talk about conversion. An equation must be dimensional consistent throughout, which means that if one of the variable is meters and one of the variables is inches, it won't work out. It must be the same unit. To convert one unit to another, write the conversion factor, and then multiply the original number by the conversion factor with the unit when substituting the values, with the canceling unit at the opposite side of the fraction when converting. So what does it mean? Is that first we need to write the conversion factor, such as 1 inches is equal to 2.14 centimeters. Then multiply the original number. It's right here, 15 centimeter. With the conversion factor, with units when substituting the value. So this is the conversion factor with the numbers and units. And the units we want to cancel out is centimeters. So we put it in the opposite side, like this. So the centimeters cancel out, we leave with inches. And the result is just 15 divided by 2.54 is approximately 5.9 inches. Okay, let's talk about uncertainty and significant figures. So if you use a ruler and measure the length at 3 millimeter, then it's incorrect to say it's 3.00 millimeter because the precision to each increment on the measurement of the ruler is 1 millimeter. So you have to say 3 millimeter plus or minus 1 millimeter. The plus or minus says that it's possibly to be the range of 2 millimeter to 4 millimeter. Okay, let's talk about significant figures. Are the accuracy of measurements. All the non-zero integers are significant, and all of the zeros in the decimal point, and they are between the significant and after the decimal points are significant. But you don't need to worry about significant figures a lot. Just write 3 sig figs. So basically, if you have answer like 1, 2, 3, 0, 0.5, that's your result, then it's safe to say it's approximately equal to 1, 2, 3, 0, 0. These two zeros are significant, but you don't need to worry about it. About out 3 figs is enough. You can put more. In scientific notation, it just some value times 10 to the exponent, where x has to be between 1 and 10. And it's useful when you're controlling sig figs or representing large and small numbers. And here's a tip. When you're using values from previous calculation, use the A and S button or select the precise value you calculated before. Do not use your rounded value. It will create errors for your final result. Round it for your final result. Okay, and this is the actual unit 1. Let's begin with scalar. Scalar is a quantity with value only, and it can be positive and negative. There's a common misunderstanding that scalar cannot be negative, but scalar can be negative. It has no direction, and some of the scalars are scalar variables, just letters such as v and d. And vectors, it's a quantity that represents both direction and magnitude. in the scope of AP Physics 1. Writing the vector with either an arrow above the letter, such as V with this arrow symbol above, or the bold letters, such as V right here. Component of vectors are scalars, and use a subscript to indicate the axis as V sub x. See here, V sub x, you do not need the vector arrow because it's a scalar. And the only really difference between vector and scalar is vectors has direction. The magnitude of vector is using this symbol here, the absolute value sign. And you may put two absolute value signs for indicating the magnitude of a vector, but you don't have to. As define the x component squared plus y component squared, and you take the square root. That is the Pythagorean theorem. This thing right here. And the theta is usually arctangent of y over x, but make sure to draw a diagram of your vectors. For example, it may look something like this. The theta is given like this. This, say that's vector A, this is vector AX, and this is vector AY. The theta here is the arctangent of AX over AY instead of AY over AX. So make sure to draw a diagram first. And adding vectors, this are a vex, meaning the resultant vector in the x direction, and the first vector in the x direction plus the b vector in the x direction, and y is the same thing. There's a tip to tail method. It's in the image right here. Right here. So basically, you are adding b plus a. You draw the b vector first, and at its tip, you add the tail of vector a. And the result is this blue vector here. That's vector c. Okay, so now let's talk about some physics. So first is distance. Distance is the amount of length of an object traveled. It's always positive. Remember, always positive, and it's a scalar. Usually it's d, but it can change depending on context. And there's a speed which defined as d over t. It use v, sometimes you use s, but it's really depending on the context. To distinguish between speed and velocity, velocity is just adding a vector symbol. Its standard unit is meter per second, and distance and time are positive, so speed is always positive. Displacement, it's the change in position, x. X representing the position. The formula is delta x is equal to x final minus x initial. The unit is meter with the direction where xz and xf. And in one dimension, you can omit the vector sign because there's really only one direction. You don't need to specify which direction it is. And average velocity. So velocity average, v average, is equal to change in position over change in time. This is a vector. This is a vector. It's a one-dimensional kinematics, so you don't need to worry about the vector symbol here, but you can if you want to put it. So it's x final minus x initial over t minus t0. In AP Physics 1 equation sheets, they assume that t0 equals 0 second. So really, you can just say it's delta x over t. Instantaneous velocity. It's the instantaneous speed, but with direction. It happened in a very, very small change in time. So what it means is that velocity, instantaneous, is equal to the limit of delta t approaches 0 of changing the displacement by change in time, and which is equal to the derivative of position respect to time. This is not tested on the AP Physics 1 exam, but this is the calculus notation for the instantaneous velocity. The acceleration, it's just a change in velocity, the average acceleration. The acceleration can be denoted by A, and there's a vector symbol here. This a vector. Average is equal to the change in velocity over change in time, which you can write it as velocity final minus velocity initial over time, where velocities are vectors. The unit for this is meter per second squared, because the standard unit for velocity is meter per second, and you're dividing it by second, which is meter per second squared. That's the SI unit for it. The instantaneous acceleration is the limit of delta t approaches 0 of delta v over delta t, and which is equal to the derivative velocity respect to time, which is equal to the second derivative of position respect to time. Don't need to worry about these two, don't worry. They're the calculus notation. They're just the definition of instantaneous. Motion graph. The slope of xt graph is velocity. Why is that? Because the slope is delta y over delta x. The y-axis is x, the x-axis is t, which is equal to the velocity. The slope of velocity time graph is the acceleration. Velocity divided by time equal to acceleration. The area under the curve of vt curve is the displacement. You can think of it in the unit form. So the unit for velocity is meter per second. You're multiplying by second, which is meter. That is the displacement. And the area, when you are solving for the area, when the y-axis is negative, the area is negative. And the area of the AT curve is the velocity. The meter per second squared times second is equal to meter per second. That is velocity. If you're calculating the average of something, you're finding the slope of the line of the 2 points on the curve. For example, here is a curve. You're finding the velocity from this t0 to t1. What you'd be doing is you're connecting a line to it and calculate the slope m. And for the instantaneous velocity, you are finding the slope of a tangent line. Basically, tangent line is a line that only touches the curve. So it's the slope at a point. It's the value of derivative. And for a constant acceleration curve, the velocity will be a linear graph. And its position curve will be a quadratic curve. And if the acceleration is a polynomial, its velocity curve will be the curve plus 1 power. So if AT graph is a linear function, then its velocity curve will be a quadratic. Might look something like this, VT. And its position curve will be AT curve plus 2 powers. which means that it might look something like this, the third power curve. Motion with constant acceleration. There are 4 UAM equations, which stands for uniformly accelerated motion equation, that we're assuming the acceleration is a constant. And we're the subscript x, meaning in the x direction, so they are all scalars. But you can change the subscript x to subscript y, subscript z to indicate the other axis. And the first three are on the equation sheet, which I will be writing it right now. The first one is the velocity in the x direction is equal to the velocity initial in the x direction plus the acceleration in the x direction times time. Second one, the position final is equal to position initial plus velocity in the x direction initial multiplied by time plus 1/2 times the acceleration in the x direction times the time squared, which you can be written it as changing the displacement is equal to the initial velocity in the x direction. The initial velocity in the x direction times time plus 1/2 times the acceleration in the x direction times time squared. The third equation is the velocity final in the x direction squared is equal to the velocity initial in the x direction squared plus 2 times the acceleration in the x direction times x minus x0. The first one is always the form in the equation sheet, and the second one is how will I write it. I will write it as the velocity in the x direction squared equal to the velocity in the x direction initial squared plus 2 times acceleration in the x direction times the displacement delta x. The fourth one is not on the equation sheet, which is x minus x0 equal to velocity final plus velocity initial divided by 2 times time, which is the average velocity times time, which means that the displacement is equal to the average velocity v plus v0 by 2 times t. I would recommend writing in v plus v0 by t form instead of the last average velocity form. This is very useful sometimes when you cannot figure out how to solve using the first three equations. And first three are in the equation sheet, and the fourth one you need to memorize it. And the zero subscript meaning the initial. And without any subscript, it means final. And now let's talk about free fall. The object in free fall, if there's no forces acting on the object besides the force of gravity, so there's no air resistance, which means that it's in a vacuum. And if there is air resistance, then it's not in free fall. The acceleration near Earth's surface is ay equal to negative g, which approximately equal to negative 9.81 meter per second squared, which is approximately equal to negative 9.8 meter per second squared, which is approximately equal to negative 10 meter per second squared. But AP exam questions are g is equal to 10 meter per second squared. G is always positive. That's why acceleration in the y direction is equal to negative g. The g is equal to 10 meter per second squared. But it's recommended to use 10. And if there is air resistance, then it will not be negative 10 meter per second squared. It will be a little bit less than that. Okay, let's talk about an example. If an object is thrown down a cliff at 100 meter, straight down with a velocity of 10 meter per second. Find the final velocity when the object hits the ground and the time it takes for the object to fall. Okay, so let's calculate. Let's list the givens. So delta y is equal to negative 100 meter because it's going down. Velocity initial is equal to 10 meter per second negative. Velocity final is unknown, and time is unknown. Let's calculate the final velocity. We don't know time, but we know velocity initial. We have velocity initial, velocity final, acceleration in the right direction, and delta y. So which means that it's safe to use the third equation. So let's use it. The third equation says the velocity final in the y direction squared equal to the velocity initial in the y direction squared plus 2 times acceleration in the y direction times change in y. And we know that velocity final is equal to the square root of velocity initial in the y direction plus 2 times acceleration in the y direction, which we can write as minus 2g delta y, which we can substitute in the value. Velocity initial squared is negative 10 meter per second minus 2 times 10 meter per second squared times our delta y is negative 100 meter. Negative 100 meter. And when we calculate this, that is 10 to the 10 times 20, square root of 21 meter per second, which is about 45.82 meter per second down. Actually, 45.83 meter per second down. And now let's calculate for the time. Since we already calculated the final velocity, we do not need the second equation. It's super long if you use the second equation to calculate everything. So let's use the first one. Velocity in the y direction final is equal to velocity in the y direction initial plus acceleration in y direction times time. So you get t is equal to velocity final minus the velocity initial divided by acceleration. So our velocity final is 10 square root 21 negative meter per second with minus negative 10 meter per second with divided by negative 10 meter per second squared, which is approximately equal to 3.58 second. Alright, let's talk about reference frames. All motion are relative. AP Physics 1, relative motion is in one dimension only. And the reference frame are assumed to be inertial, means the acceleration of the reference frame is 0. A non-inertial reference frame is the reference frame is at non-zero acceleration. Let's say there's two cars A and B, which moving velocity AE equal to 40 meter per second, and velocity BE is equal to 20 meter per second. And first subscript letter is the current object, velocity of object A, velocity of the object D, and the second letter is the reference frame. It's on Earth and on Earth. So in Earth's perspective, a person is sitting on Earth and looking at the object. This one's moving at 14, this moving at 20. And velocity of car A relative to car B can be denoted as velocity AB, and car B relative to car A can be velocity BA. And the fact is that velocity AB is equal to the velocity BA. The negative in this context meaning the opposite direction to each other. And it only applies when it's in the vector symbol. the velocity AE is equal to AB plus BE, and BE is equal to BA plus AE. The second letter of the first velocity and the first letter of the second object is the same, so we can say that these two are the results, B and E. And here's an intuition. It does not guarantee it's correct, but it makes better sense for you. So for the first one, velocity AB is equal to velocity AE minus velocity BE, where 40 meters per second minus 20 meters per second is equal to negative 6 meters per second, which makes sense because car B is moving faster. Those people in car B looking at car A is moving backwards. So basically, VAE plus equal to VAB plus VB, you can think that vector starting at A, having transition at B, then arrive at E, which is A to E. It's not really correct, but it kind of makes sense for you to understand what is going on here. And our final concept is projectile motion. Projectile motion is a special case of two-dimensional motion that has zero acceleration in the x direction and non-zero acceleration in the y direction. The motion can be treated separately. In projectile motion, initial velocity can be separated into vectors into components using trigonometry. If theta is the angle from horizontal, then velocity in the x direction equal to velocity times cosine theta, and velocity in y direction to velocity and sine theta. If the theta is from vertical, then we swap sine and cosine. But make sure to draw a diagram of the force vectors and break it into components using trigonometry. And use UAM equation to solve for the unknowns. And here's an example of it. An object is thrown upwards with an initial velocity of 5 meters per second upward with the angle 26 degrees from horizontal and an initial height of 30 meters. So we're going to do first is draw a diagram for it. So this is the change in y is equal to negative 30 meter. This is change in x, which is unknown. We are 26 degrees from horizontal. So let's 26 degrees from horizontal with initial velocity 5 meters per second. And calculate the final velocity. So velocity final equal to question mark. Calculate time ball in the air. T is equal to question mark. And the horizontal distance, delta x equal to question mark. So what we're gonna do first is break the velocity into components. So velocity initial in the y direction is equal to 5 times sine of 26 degrees. And velocity initial in the x direction is equal to 5 times cosine of 26 degrees. So now we can use UAM equations. We see it's the same situation as the last question, where there's no time given, but we got the final initial, we got the acceleration in the y direction and the displacement in the y direction, which means that we can use the third UAM equation to solve for the final velocity. So velocity in y direction squared equal to velocity in the y direction squared initial plus 2 times acceleration in y direction times change in y. So we don't know what the final velocity is, and we know everything else. So let's solve for the velocity final in y direction is velocity plus 2ay delta y. So we can substitute in values. The square root of 5 sine of 26 degrees squared plus 2 times negative 10 meter per second squared times negative 30 meter. And which is, let's see, that is 5 times square root of sine squared of 26 degrees plus 24 meter per second down. We're not going to round it first because we need that result. It's asking for the final velocity, and the velocity is the vector, so it has both x and y component. And we're only solving for the y component right now. We need also the x component, so we can use the magnitude formula in the very beginning, where velocity, magnitude of velocity equal to velocity in the x direction squared plus velocity in the y direction squared. So that's the velocity in the x direction has a zero acceleration, means the velocity will never change, which means the velocity final equal to velocity initial. So that's 5 cosine of 26 degrees squared plus Vy squared, we just solved for it, 5 square root sine square of 26 degrees plus 24 squared, and having the square root here. That is about, let's see, that's actually exactly equal to 25 meters per second. And that's our result here. Next one is calculating the time. So the same process as the problem above, where we already solved for the final velocity. So we can use the velocity in the y direction equal to velocity initial in the y direction plus a in the y direction times time, where t is equal to velocity final in y direction times minus velocity initial in the y direction all divided by acceleration in the y direction. So that's that is, let's see, it's y direction, so that's -5 square root sine squared of 26 plus 24 meter per second minus velocity initial, which is -5 sine of 26 degrees, all divided by -10 meter per second squared. That's the gravitational acceleration near surface of Earth, which is approximately equal to 2.24 seconds. Okay, that's the result for time. And the last one is change in x direction. So delta x, we got time, we got the initial velocity, we got 0, we got time and initial velocity, so we can use the vx0 t plus 1/2 axt squared. That is the, I believe is the fourth one. Let's see. No, it's the second one. The second equation. So we know that acceleration in the x direction equal to 0 because there's no force acting on the projectile except for the force of gravity, which is pointing straight down. So acceleration in the x direction equals 0, so that's the whole thing 0. So delta x equal to velocity x in initial times time. So that's 5 cosine of 26 degrees. For the time, you want to use the exact value. So press the answer button in your calculator, and which is about 2.24009121371 second for my calculator. And so that's about 10.067 meters. And that concludes my review for AP Physics 1, Unit 1. Thank you for watching my video, and please like and subscribe.